Okay, hello everybody. So, what is the gradient? I guess nabla f or grad f. Sometimes people write grad f, but this is an upside down triangle. Okay, so what is it? So, given any function whose input space is whatever we want, any kind of inputs, but then the output has to be just one real number. Okay, so we've seen functions like this, like x squared minus y squared. See, the output is just a real number. We've seen functions like this, x, y, z goes to 4x squared z minus 2xy plus 7. So this is just one number. And so to every point in space, to every input point in the space Rn, it assigns a number. Okay? And we've seen that, like, in the input space, we could draw the input space. Like, let's say the input space was just R2. Then we can draw the contour lines. Like, these could be all the points that are assigned to the number 5. And then these could be all the points that are assigned to the number 3. And maybe all the way over here, now we start getting negative numbers, like negative 1.1. And over here, maybe it's even further, probably like 7.8 is over here. So these are the contours, or the level sets. And what happens is we're going to define the gradient, and the gradient will also be in the input space, and at every point, it'll be 90 degrees. At every point, it'll be 90 degrees to every single one of these contours. 90 degrees. 90 degrees. And it'll always be pointing, so it'll be pointing grad f at a point, I think I'll just say grad f pointing in direction of maximal increase. So it's telling you, where should I go to increase the function value? Grad f says where to go to increase the value of the function f. But what is grad f? I didn't even tell you it yet. Okay, so remember, it can take any sort of input space, and then we're going to visualize it by putting a vector at every point. A vector goes at every point, and there's a contour line. It'll always be 90 degrees. Okay, so let's think about a function and how we get its gradient. So for any function, we can look at the Jacobian matrix. So maybe I'll do this over in pink. The Jacobian, well, in this case, it has how many? N columns. Or really, it has one column for every input. For every input. Because we can take partial the first variable, or we could differentiate with respect to the second variable. We could take the partial derivative with respect to the third variable, all the way to the nth variable, xn. And we put them in columns of a matrix. Now in this case, because the output, if output is just a real number, then each column, has size 1, has only one number in it, only one component. Okay, so let's do an example. Like if we had the xy mapping to x squared minus 2y squared, then the Jacobian would be, well, partial x, give it 2x, and then partial y is a minus 4y. So the Jacobian has, one column for partial x and one column for partial y. But you see, there's only one number in each, okay? And so what's going to happen is that we can now interpret this as a vector. So this whole row. So the Jacobian will have, if the output is r, each comma is 1, aka the Jacobian has one row. Has one row of length n, which is the dimension of the input space. Okay, so we can interpret. Nobody can stop us from interpreting that row as a vector in the input space. Okay, so in particular, at a given point, at let's say p equals 3, or how about, 3 comma 1. Then I plug in a 3 and a 1, and I get, 6 minus 4. So I interpret this now. Interpret as a vector 6 minus 4 in R2. That was the input space, R2 to R. And so in the input space, I can go to the point 3, 1, and then I can put this vector 6 minus 4, so it's like that. There we go. And this is the gradient. The gradient is do this at all the points. Pick another point. This one looks like, -2, -2. And so I plug in at, at p equals -2, -2. Then what do I get? Well, my Jacobian matrix becomes 2 times -2, and -4 times -2, so that's 8. And so I interpret this as a vector, -4, 8, in that same input space. And so right here I'll go -4, 8, and I'll put this vector. Usually I don't. That was just to help me draw somewhat of a realistic picture. And so you can see that this can happen. We can take other points everywhere and just start putting vectors there. Okay? And this is the gradient. So what is the gradient? So what is the gradient grad f? So given any function from any inputs, but the output has to be just the real numbers, grad f is a map, a vector field. It is a map. Well, what's its input space? Actually the same. But now, the derivative would go to R. But that is not what's going to happen. This is not the derivative. The gradient is not the derivative because it doesn't have the same output space. It has a different output space. In fact, the output space has the same size as the input space, and that's what makes this just a very different map than the derivative. Of course, it's related. It's got the partial derivatives in it. That's how we form the gradient. What do? Well, we take a point, x1, x2, up to xn. And where do we send it? Well, we send it to, we had this map, f, like completely separately, we had a map. So for any point, we can calculate f of x, right? And that means we can also take the derivative, like the partial derivative with respect to the first variable. We can also take the partial derivative with respect to the second variable, etc. And that's what we do to make the Jacobian matrix. So now, what's our map? Well, we're just going to put this partial f, partial x1, comma, partial f, partial x2, comma. And we're not going to plug in until later. And so these are the formulas for the gradient the gradient vector field. And, this is not new because we'd already been computing the Jacobian matrix in order to interpret its columns. And now we're just sort of reinterpreting its rows. And the main thing is that to the input space of the original function f, we are going to now create a vector field that assigns to every point a vector. Every point gets a vector. Every point gets a vector. It's not a random vector, it's a very particular vector formed in this way. So I took this function, I take the partial derivatives, and then if I want to know what's the vector that goes here, well, I plug in that point. It becomes an actual vector when I interpret it as a vector, and that will tell me what vector to draw. Okay, that is the gradient of a function whose output is one real number. The gradient is a map. It is a vector field.